So today we have Dr. Mohsen Esteghamati. He's an assistant professor in the Department of Civil and Environmental Engineering at Utah State University and the Seismic Resilience lead of Utah Earthquake Engineering Research Center, UEEC. His research interests include risk-based assessment of engineering systems, generative performance-based design, and the interface between digital and physical infrastructure. Previously, he was a postdoctoral associate in the Department of Civil and Environmental Engineering at Virginia Tech, where he also received his PhD in civil engineering. Prior to that, he received MS degree in statistics from the University of Akron, in structural engineering from American University of Technology, and a BS in civil engineering from Iran University of Technology. Also, he is a member of several ASCE, SEI, and ERI committees and served as a co-chair of SEI's Risk Assessment and Decision-Making Task Committee. Also, he mentioned that he has a session in an EMI. If you are interested, you can go for that. Today, Dr. Esteghamati will present on a really wonderful topic, explainable machine learning models to accelerate performance-based design of the structural system. By this brief introduction, Dr. Esteghamati, floor is yours.
Okay. Thank you so much, Paisa. This was such a nice introduction, and thank you, GSC, for having me. So excited to be doing this. So let me first do this check and see if it's gonna work for us. Can you folks see my screen? Okay, beautiful. All right, thank you. As I was talking to Paisa before this, I would hope to make this more of an interactive talk. We can stop at any slides rather than me just talking for, 45 minutes. With that being said, the kind of flow of the topics that I was thinking was just talking a bit about the motivation of why we want to use machine learning for performance-based design, show you some proof of concept that it can really work, and then talk about explainability a bit, and then talk about the extension of these approaches to fire domain, which is something new that I've been pursuing with some colleagues at Johns Hopkins University. And then, it won't be a machine learning talk if we don't talk about generalizability. So I just wanted to talk a bit about that and bring everything together, if we can, if we have time for that. Really, the big motivation of my work is that I always think, what is the role of structural engineers in this world with increasing frequency and intensity of hazard, right? And we tend to think in terms of community resilience goals. It has so many components and so many different people needs to work, environmental systems, economic system, governance, right? And when I look at this, I see structural engineers as this small box on the bottom, right? We are trying to work with some other engineers and stakeholders. And what I really worked on myself was individual buildings, though there are structural engineers that works on critical infrastructure, transportation networks, or lifelines, right? Now, being a small part of a big thing is never a bad thing, right? That doesn't mean our contribution is small, because the way I think about this is that we have this very complex problem in front of us, right? It's all about how we can bring this design and assessments together, where we can think about initial construction, operation, hazard, and aging and deterioration of the systems, and then connect all these different aspects of our infrastructure to think in terms of performance metrics. Now, what I was really interested in was resiliency, but also sustainability. And these metrics, I think in the future years, irrespective of how we think about them, gonna be very important for the science. Now, for those of you who may not have heard about performance-based engineering, is really a way of thinking about systems, is a probabilistic and modular framework. And typically, it came originally from earthquake engineering world, but it has been applied to all other different hazards. To some extent, for some other hazards like wind, we have a very well-defined performance-based engineering system. But for some other hazards like, maybe tsunami or, hurricane, maybe it's not, all the modules are still under active research, right? Now, in all these different frameworks, there are some commonalities. They all have a hazard analysis, which talks about the intensity, frequency, and the exposure that the system's gonna get from this hazard. it always has this structural analysis portion that talks about how the system will behave to the intensity and the frequency of the hazard. And then what I call loss assessment, though that's a loose term, this is really trying to connect the damage and the responses from the systems to what's going to happen on the decision making side. And this can be repair time, recovery, downtime. Maybe you've heard about functional recovery. There are many, many metrics that are becoming increasingly important as we start to think about the community resilience. Now, how did all of this started? Really, when I started my PhD in 2018, at that time, my advisor was like, well, you seem pretty interested in this and you really like machine learning. And at that time, full disclosure, machine learning was there, but it was not, it was before the generative AI, boom of machine learning, right? So at that time in 2018, I thought maybe I can bring everything that I like under one unified system. And the idea was like, can we use machine learning to support performance-based assessment and design because they need a lot of different kind of simulation, many components that goes inside these frameworks. And we thought that maybe by using machine learning, we can create surrogate models. And these surrogate models can serve as some computationally expensive mappings for us to ease the burden, at least at some point. So it becomes actually an interesting problem of, okay, what are the steps that we want to use machine learning and what are the steps that we want to keep as a physics-based kind of an approach. And then I had this idea, which at that time my advisor was kind of very suspicious about the idea. And the idea was that maybe, people are looking at the nonlinear responses and connecting that to the system's properties. But, I had this experience as a structural designer. So I was like, can we just focus on design parameters and geometric and design parameters of a system and connect them directly to the decision making systems, right? Now naturally the question was like, well, a lot of error sources gonna propagate, and then maybe we don't get a good mapping, right? So this is how it all started. I'm showing here really the original idea, which was, well, what if I create this database of simulations in a very specific way that can support the kind of data that I need, and then use a conventional machine learning paradigm that, split the data, train the algorithms, do hyperparameter tuning through some hybrid methods of grid and randomized search, and then do some cross validations and then use that to understand this data, right? Now, this is very conventional, and I think probably many of you who have used machine learning has seen this, right? But really the big idea was that what is the kind of data that can support this mapping that I had in mind, right? Now, back in 2018, I think like Design Safe by NHERI and Texas and Tech, right? They were pretty new and people were starting to put data there. So I started to look for the data that could support my work. And there were not many open data sets of finite element simulations of engineering systems and even buildings, which was the topic of my NSF project. So eventually I had the idea that maybe I should create the data and do this. So it started by creating some computational tools and then connecting them in this, infrastructure that can go all the way from, and I don't want to call it a very exact design, but it was more of trying to sample these design parameters, then try to do some checks to see if they're even feasible from some initial checks, and then do some sort of a nonlinear analysis to see if the life safety objective of the code is met. And after that, would keep that design and do all other performance-based kind of assessments that I needed at that time. Now, I will be happy to talk about this, but I'm just trying to keep it short. We did this and it was very interesting because the place that we chose was in Charleston, right? Now, if anybody has worked with Charleston, it has a very interesting seismic situation with a negative epsilon, which means that selecting grand motions, it's not like you can like we have places like California, which there are well-defined databases of grand motions. Much research has been done on that. But for Charleston, it was not like that. And at that time, one of our challenges was to find grand motions for that characteristic earthquakes that we expect at that place, right? And then we work with some seismologists at Virginia Tech. We eventually ended up using some synthetic ground motions to be able to do the analysis that we wanted to do. With that being said, just to, and this is back in 2021 when the paper got published, right? We went through this process, we get our data, we put that data into this machine learning pipeline, look at a few classical machine learning algorithms like support vector machines and random forests and all these different algorithms. And we saw that actually we can do this mapping, and this mapping can provide a good accuracy, right? Like something, and again, I don't want to make this more about, oh, 96% accuracy, so we did a good job, right? It was more about we saw that we can capture this performance across a good range of the value that we were looking. Now, if you're wondering what did I capture something called EAL, or expected annual loss, which is basically having an annualized repair cost of the building for the possible earthquakes in that region, right? And this is a metric that has a lot of use for decision making. And our idea was that what if we use it directly as a design target, right? And if we can find the designs that match to a target EAL, then imagine the implications. Like in future, communities are having structures that are not just built based on a, life safety, not collapsing on people, but more of like, well, if these earthquakes that we expect in this place, we can keep the economic losses to a certain threshold, right? That would be beautiful if we can do something like that. Now, as soon as we did that, I started to get interested that, well, I have this support vector machine, right? This is a block of code somewhere that does this mapping, but it's just hard to communicate that. It's hard to understand what is happening inside this model. And if you've seen support vector machines, it's just like what? Like a kernel being applied, and you're trying to find this decision boundary and then trying to pick the data and putting them at the right place, right? It's very hard to communicate that, and it's hard to understand what is impacting things, especially in a design problem. This will become super important, because one of the first questions in the field is that, well, are you sure that this is using very meaningful features, right? Is there any meaning to what the model is predicting? No, at that time, what I did was really sensitivity and not explainability. And this is something called variance-based sensitivity, right? Or Sobol indices. Maybe you've heard about that. But basically, we did a kind of running a lot of these models and then measuring how the variance in each of the features of our model is affecting the variance. Is there a question maybe that I'm missing? Okay. How is that affecting the variance in the output? And what we saw here, the black columns are the first order, and the white columns are the total effect coming from all the higher order interactions. And we saw, though the number of features with a strong first order effect is small, all the features in the model had higher order interaction, which to me was a sign that this mapping is actually pretty complex, because all these features are having high second or third degree interaction with each other. And that was kind of like a motivation that maybe I should go a bit deeper into explainability of these models. Now, when I started in my new role, one of the first thing I did with my PhD student Shiva was like, well, we did it for one database, right? But maybe, I make the database with my own biases in a way that could support this mapping, right? What if we can find an independent external data set and try this method on that, like try the same mapping? Now, the good news is that over the years, DesignSafe is now full of data. So if you're a graduate student doing research, I strongly encourage you to look at the DesignSafe. Everybody in the community is helping, and there are so much valuable data. Often we don't know what exists there, but I think you may find something that can be very useful for your projects. And I also invite you to publish your data if you can. Talk to your advisors and see if you can publish your data there. This is what I tell all my students, that we should publish them. Anyway, so we looked at this database of still frames by Dr. Burton's group in UCLA. We've used this database, extensively in our recent research. But basically, my own research was on concrete frame in Charleston. Now we have this database developed by a different group of still moment frames in Los Angeles, different designs, different ground motions, difference in many things, right? And we start to look at more design and geometric features and more metrics besides EAA. We start to look at fragilities and recovery and more stuff in that database. And then we saw the kind of the same thing that we can pick several algorithms and some algorithms still can do the mapping. Actually, quite interestingly, is that the same support vector machine and random forest that was working in my data set with like 90% R square kind of was doing the same thing for this database that was independently generated by a different person. To me, this is a good measure that this approach is not limited to one data set and how we are building this model. We can map these designs to the performance metrics and have machine learning models that can work within the ranges of the parameters that we're looking at. Now, this is basically, I want to put this cautionary tale that we, as engineers and scientists get excited about algorithms, but really from an application perspective, a lot of times you see these algorithms perform relatively similar, right? So I think, it's important to understand that it's more about the feasibility of doing these mappings rather than, oh, it must be random forest or it will not work. I don't think it's like that. I think like there are many suitable algorithms that can do the mapping for us and they're going to have comparable accuracy. Now, I want to talk and start to talk about this explainability. We in TC, well, it used to be called task group, but I think now it's task committee. In TC3, which I'm co-chairing, which is the risk assessment and decision making, we started an effort to look into the literature on explainability in computer science and statistics, and then think about the work in structural engineering risk-based assessments. And then what we saw is that, there is a wealth of literature. Even I feel like we are in a very preliminary and important spot on this, which is that even the nomenclature and terminology, there are so many words, and we need as a field to come together and be like, okay, what is our perspective into explainability? Now, you probably heard explainability and interpretability, and in our field, we use them, interchangeably. But one thing that I like as you go to these fields in computer science, there is a huge discussion to distinct these two, right? And explainability is usually, and they consider this an interface between the machine and human and explanations that should be comprehensible by human. So it's kind of like a post hoc approach. Whereas interpretability is to the degree which a human can understand a AI model, and they consider this an intrinsic property of the model, not something that you can make it happen for you post hoc, right? So even the way we think post hoc, ad hoc, and then there are so many other terms, transparency, trustworthiness, and how people think about this. So I think, and this is an invitation, if you are working in this field, I would love to hear your thoughts on this, right? Maybe as a field, we should come together and come up with a schema and with a taxonomy. And then on the right, you see the taxonomy that we did some literature review and we created some sort based on other people's taxonomy and saying like, well, there are many different taxonomies to even think about the concepts in this field. And maybe we should be like, oh, do we want to get a functionality based taxonomy? Do we want to get a conceptual based, a result, or something that some other fields are doing, which is a hybrid of these taxonomies? Now, I can go very deep into these conceptual nuances, but if you allow me, I would like to go back to what we usually see in the field. By the way, probably you have seen this. This is called a Shapley explainers. If you haven't seen this, basically the idea is coming from game theory. We say all the features of the model are players in a game, and the prediction is the payoff, and then we try to be fair to them. So if two features contributed equally, we give them fair credit from the payoff and so on and so forth, and then use that to say, okay, how much influence these predictors have on the prediction, right? And typically, one way to read this is that as you go left to right, the value of the feature is increasing. The color code here, blue to red, the value of the output is increasing. And with that, you can understand how things are affecting things, right? Now, we did the literature review. We looked at a lot of papers in the field, and SHAP-plot is, in our understanding, number one approach that people are using whenever they talk about explainability of machine learning model. I want to emphasize that's really a post hoc approach, a good one, but just one way to think about explainability. It's not the only way to think about this matter, right? Now, as soon as I started to look at this SHAP plot with my students, right, we can see some interesting stuff. I call them the sanity checks. The plot on the right is the median of a fragility. And if you know what is a fragility, it's the likelihood of a damage of the system, right? And we can see that what is the most important feature is this is sorted by that, right? Is the first one, which is T1, which is the period, right? This is very intuitive. These fragilities are based on the SAT1, right? So you would expect that. And we see that the model is also doing that. So that's a good sanity check to know that the model is doing what we think it should be doing, right? Now, if we get some comfort and confidence in that, then we can start to look at features that are not as intuitive. Like, for example, an example that I have on the left, we have EAL. And then one of the parameters here that I want to talk about, if you look at this, for example, ICI mean, this is the minimum of the moment of inertia of internal columns. Now, in a regular design, it's very hard to imagine what is the relationship between this component level design parameter and the global EAL. But with machine learning model, we can see that, for example, for our cases, the impact was much lower than many other parameters. But also, as we increase this, the EAL is decreasing. So we basically want to increase the minimum moment of inertia we are picking for internal columns, right? And this is a good design guidance to give to the designer that wants to do performance-based assessment. Now, one other things that I want to talk about is that, again, there are other kind of explainability techniques. There's something called accumulated local effect. This is really looking at the features impacts on the average prediction. And there is a way under the marginal distributions that we do that and then the center this. And the good thing about this is that we can bring numbers into this kind of thinking about parameters, right? Now, as these three parameters that you see here are all design parameters, IB mean is minimum of moment of inertia of beam, so on and so forth. And I don't want to get into the details of this, but one thing that I want to emphasize is that we see different trade-offs. We see some of these parameters, as you increase them, things get increased, the EAL get increased and then flatten out. One of them gonna decrease the EAL, but after a certain point, it's gonna increase that. As soon as you see this trade-off, the first thing that comes to mind is that, well, then we can write an optimization problem and find the best combination of these features that can really give us a good performance-based design. And this is really something that I did last year, this got published. And the idea was like, can I use these machine learning models that I can understand and use them as an engine for optimization to solve the inverse problem? Basically saying, well, I have the geometry, you give me the design parameters that can get me to a target performance. And no, that would be, in my opinion, a game changer, because instead of the iterative process that we have right now, no, we can solve the direct inverse problem. And this is really because of the machine learning and not because of the optimization, because the machine learning is the engine, is the function, is the fitness function here, right? And if you're looking at this, you see what are the parameters I'm picking. IB mean and WT, these were the most important parameters that we were understanding over this. I want to be mindful of time, so I'm going to go a bit faster because I have only 15 minutes. I want to just talk about the extension. So some of my colleagues, I brought this to them. I was like, hey, we are doing this in earthquake engineering. What about fire engineering? Do you guys have interesting, stubborn problems that we can apply this? And Thomas was kind enough to talk to me about this. And we start to think about this fire resistance of timber columns and how, we need to do these costly, expensive experiments to understand this. So we trained some of these models, very same mindset, just kind of a different data set of experiments on the fire resistance of these timber columns. And we saw that it works very well in that application. So then Thomas and I, we were very interested to understand, okay, what about the explainability? Would the model still pick something that from fire engineering we think should be meaningful? And this was the most interesting part to us. So we know this in these timber columns, the outer layer get charred and then put insulations, and that helped the column to carry more loads than what we think it should carry under this fire curve. And we start to see that the most important parameters was the capacity of the column at the ambient temperature, which is what we expected from the physics of the problem. And we see that the model is also picking on that. And then we see that the material properties were not super important. And we see that the dimensions are very important, which basically tells us really the loss of the section is what is influencing this problem. We started to look at the composite flooring system. This is something that we are writing as of now, so this hasn't been published or been even sent under review. But here's a sneak peek into this. We are starting to look into flooring system, doing the same thing, trying to understand what are the parameters that influence the fire performance of these composite flooring systems. Okay. I'm going to use my last 10, 15 minutes to talk about something that I think can be super important. And that's like, as soon as we talk about machine learning, we show the models, we show the performance, always you're going to get this question, yes, but is it generalizable? And by that, people usually mean, okay, if I take these models, bring it to a different problem, would it still work, right? Now, I had the same question back in 2023. This is the last thing I did as a postdoc PhD. And I said, okay, I have my database. What if I go and create a sample, totally different geometry from what was in my sample and a bit of a different kind of approach to the design? Would my model work well, right? So my models were between 4 to 6 on the training day. I got a two-story. And those of you who are coming from earthquake world, you know that the short buildings do very different and dynamic than the mid-rise buildings, right? You're going to that pesky part of the design spectrum, right? So we did that, and here the circles are machine learning, the triangles are a simple single degree of freedom system. And this was quite interesting. So I saw that sometimes my machine learning model definitely do a better job than a single degree freedom system, right? And by the way, these are not super simple single degree freedom system. We calibrated that based on pushover. So they had a bit of help from the nonlinear world, right? But still, uh, sometimes we are just close to them, but ooh, I get excited. But sometimes they're pretty far from the what they should be, right? And this is what people usually observe and make them suspicious. They're like, oh, there's sometimes it's machine learning models, you change things, they can really go wrong, right? So I started to think about, yeah, we can see this. And one of the remedies is like you're gonna be like, well, my machine learning model only works for this range of parameters. You shall not use it for anything else, right? But I was like, can we do something to make it a bit better so that's at least less sensitive? So I want to also talk about this, which is a bit different from generalizability, but a problem that some of you will see. I call it, well, not that I'm calling it, it's a standard term in computer science, is under specification, which is different from underfitting. So under specification basically means that if you have an overly parameterized machine learning model, you can find different combination of the features that both of those models will work very similarly when you train them. But as soon as you take it to an independent test set, they're going to act very differently, right? Because you're not really defining your problem in a unique way and your model is under-specified, right? And I want to say that sometimes the issues that you see in generalizability is under specification, but not generalizability. So be aware of that. And if you are interested to know more, here is a paper for you that was editor choice. So some brag there, but hopefully that can be useful to your research. And we start to talk about this under specification and generalizability. And I have this very smart colleague in statistics, and he was basically saying me like, why do you guys always use this randomized split of training and testing? Your data sets are so small. If you do a randomized split, how do you know you're capturing the important data trends, right? So we started to do an adaptive sampling and basically saying, well, I know my important parameters, right, from the physics of the problem. Let me make sure that distribution is kept in my training and testing. And as soon as you do that, something interesting happens. A lot of models that you think are not generalizable are not trained properly, right? But if you do this on the split and then train them, you're going to see that their performance on new data sets becomes much, much better. The other thing that I want to talk about, this is a very interesting and exciting topic, is how can we embed physical constraints into our models, right? Back in 22, we did something on really thinking about bringing physics embedding into the data, right? And having inputs that are having these physical embeds. And we did some fancy stuff with error tracking and making sure the errors are always being corrected by the physical embedding, so the loss functions can account for that. And we show that as soon as you do that, it really helps with having models that are more generalizable. And I want to just mention that I think that one of the good topics in the next 5 years is like, how can we create physics informed machine learning models? What is the right integration point for our models, especially the kind of small data sets that we have, right? Because not all of these strategies are going to give us the same. They're super sensitive to how we think about this physical embed. Now, this is very new thing that my student Parham and I, we are thinking about this. So we are we are going into this generative AI. So because so far everything that we did is the discriminative AI, which is, input output mapping. But we are thinking, can we create this generative AI the way that ChatGPT generated things for me? This guy generate design for us. But of course, we don't want this guy to hallucinate and tell us designs that are not realistic. So we are kind of thinking, how can we embed physical relations into this generative model, which is a transformer model, right? We started to do some stuff, and the reason I'm showing this is a very early stage research and it's not super successful, right? We are just trying this. We see some promise compared to a baseline model. This is a bit better, but still, the red circles here are this very complex model that we are building, and then basically the blue square is a support vector mission from my previous research. And we see that when we get to this interesting region of the data on the end, still both of them are not doing what we hope so, right? The good thing is that by doing this physical embedding, before that, our transformer was sometimes generating very strange designs that was definitely questionable. But with this approach, we remove those very fake designs. But now we are on the next improvement stage. We are like, okay, can we now make it much, much better than a purely data-driven models? And I think I have a few minutes. So I think like our idea is what we call privileged information, and maybe that can be useful to some of you, is basically we're going to create this teacher model. We're going to give it all the information needed, right? Physics, embedding, everything. Then we're going to do a knowledge distillation and create these smaller student models. But these student models will not see the physical embedding, right? Which is the privileged information. They will just see the kind of inputs that's available at the design stage, which is pretty limited, right? And our idea is that if we can do this right, these student models inherently has this, I'm going to call it feeling, but that's not a scientific term. They have some feeling that, well, this combination of inputs, I haven't seen it from my teacher. And the teacher do this because it's seeing the physical embedding, but the student doesn't know that. It just knows that certain things cannot go together, right? And we hope, I think it's a pretty niche idea, but then I'm biased. But I think like if we can get this right, it has a lot of implications because a lot of times we need models that are trained on more data, but are able to be working at the places with incomplete information. So if you're working on something with incomplete information, I invite you, please think about this idea and see if that can have some relevance to your work. And my last note, I'm gonna end it on a question. So if you're not from the earthquake world, please bear with me. But whenever people talk about machine learning, the opposite is finite element analysis, and a common method is plastic hinge model with what we call IMK calibration, right? And basically, this is a gold standard. Oh, this is a very physical model, right? You're putting plastic hinges, then you're putting this relationship based on previous experiments. So I want to show you two things here. So look at the plot on the left. Do you think that the dashed line, especially the dashed line on the bottom, is a good fit to the data that you see? And the data is all these diamonds. And then on the right, tell me if you see a decreasing trend, a real decreasing trend, as people are showing with this dashed red line. Okay? And you can unmute yourself and tell me yes, 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 no, no, no. What is your opinion? Ooh, silence. Okay. I will argue, I see some stuff coming in the chat, so I cannot read that. But I would assume I asked this in a workshop, in Phoebe workshop in Nebraska. And a lot of people were like, well, I don't really think the dash line is getting the data, especially if you look at this for the data, there is a portion on the top of the plot that is very far from this dash line. And then the decreasing trend, really, if I remove that 4 data points on the left, then there is no decreasing trend, right? It's a buck of data, right? No, you would be surprised to know the equations that were calibrated to the experiments. I just put a box there. You see the same thing being captured in them. So this, physical relationships are coming from people fitting these very simple linear models to that experimental test. And if I show you this, you may, again, I don't want, like, I think they did a fantastic job. I think this is pretty good way of dealing with the data. I'm just saying that as soon as you see this, one can argue, well, is this model really generalizable? Is it really capturing all the data points that we see, right? And the short answer will be no, but it's capturing the majority of the things that matter to us, and it's a good approximation. But we are very comfortable doing this kind of justification when we see a linear or a nonlinear regression. If machine learning model does the same thing, people start to shout, wow, this is not generalizable. It's not capturing this one single observer. Yeah, it's not capturing that, but is it capturing the majority of the important thing? So I want to end this talk by saying that a lot of times when people talk about generalizability, I think it's an explainability issue in disguise. And because we cannot show them what is happening inside, people are more, well, they're, I guess, a bit reluctant sometimes to accept how the model is working. But if people could really see this, then they can make an informed decision and be like, well, it seems that your model is getting this pretty good. So if I'm applying it to this data, I'm good. And if I think about this part of the data, then maybe I should be more careful or not use the model. And with that being said, thank you so much for having me. Hopefully I was on time. I think I was, but I will be very happy to answer any questions you may have for me.
Thank you so much, Dr. Esteghamati. It was interesting presentation. I would invite all people to freely open their mic, and if they have any questions, just feel free to ask it. I have two for mine. I will wait for others.
Sure. It's just always hard to be the first person to ask question in an online meeting. Yeah. It needs a lot of courage to do that, right?
Yeah. Okay, I will start by mine. Um, when you were talking about the explainability, whenever I think about this problem, for me is that it is going in the future being a deployable workflow that is going to be used, for instance,
Mm,
by some firms or policymakers and agencies. And my question is that for those people, how these machine learning models become explainable? For instance,
mm,
are they looking for some uncertainty safeguard or
mm.
some physics consistent behavior in a model? What should be considered for them?
Yeah, no, this is a fantastic question, but I think I always have the same kind of a thought when I'm approaching this. And my experience, I've been trying to communicate some of these models at different communities. One thing I notice is that it's very community dependent for some reasons, right? You go to policymakers, you bring a shot plot, you lose that argument right away, right? Like you want to put things in a bullet points, very clear language, right? You go to an engineering community, they're very interested on the physical concept. They
Yeah,
want to make sure that your model matches their engineering intuition. Like I had this conversation with an older gentleman that did, seismic design for 25 years, I think, right? And what he was very interested was not fast or those like giving them a fast tool. That was not their thing. It was like, can it, also mimics some of his intuition and experiences in the way that he would do. So he would go really into like, oh, what are the sections your model is producing? Like, can you
yeah,
show me like why is it not getting this uniform section, right? These were the questions. So I think what you're alluding to is a very important topic, and I think it really depends on who we are talking to. My last caveat is that also, as we talk about these approaches to explainability, there are also mediums
yeah,
to present this. And I think something that would be super useful to all of us is, understanding how we can do better visualization, better
yeah,
representation of this. Like it's not enough to, create a, I don't know, ICE or a
yeah.
partial dependence plot and feel like, oh no, I can go and explain this, right? So uh, many things. Hopefully I touch base on some of the things in your
Yeah, yeah,
mind.
yeah, yeah, yeah. That was really good. Thank you. Also, we have one question in chat. I will read that for you.
Sure.
Mustafa asked, how do you recommend linking model outputs like EAL fragility to GIS layers, like building parcels, lifelines, so the results are usable for planners, not just researchers?
Oh yeah, no, ooh, that's a very good question. Okay, so there is like a few things there. Like I think like one of the first thing is what like when we think about the fragility, there are different ways to express that, right? Like, are we gonna go and get some, central measure of the fragility, right? Or are we gonna get some dispersion measure of the fragility? Now, some measures like EAL is much easier to do that linking because you have a single point, right? That, is also normalized. So it's much easier to talk about that. And typically the kind of things that I did on this GIS application is that they define the EAs in terms of the initial construction or housing value and basically say, okay, this normalized percentage, I'm going to link that to the coordinates that I have on my parcels, right? And it's much easier to talk about, well, if a natural hazard happens, 25% of this region gonna experience, a loss of 30% of their original value, right? Like that is pretty easy to communicate to planners, right? The fragility is a whole different topic, right? First of all, Mustafa is a very brave person that wants to do that, right? And I think like it comes back to anytime you're trying to communicate a probabilistic measure, there is some challenges. One thing I learned is that maybe, we should come up with a single proxy to talk about that. And really the best one are not dispersion one and more of central measure one and basically talking about median fragilities, and again not calling them SA exceeding blah 50% of the time, but something that the FEMA tried to do when they define like a term and say, well, this is the collapse capacity, and then link that to the fragility, and in all the communication it was collapse capacity, which was much
Yeah,
easier to come. I don't know if the question was more on the communication side, but if it was, these are some initial thoughts on that.
yeah, yeah. Thank you for your answer. I have one more question.
Please.
Um, when you were mentioning the how we can have a model that is
Mm,
generalizable, and you touch on the fact that sometimes we have data that is incomplete. I want to also touch on the fact that we have also the cases that data are scarce,
mm.
and in those cases the term being generalizable is difficult to be defined. What is your opinion on that?
No, yeah. Very, very good thought. So I think like this goes like on those terms, like especially when we have this limited data. So it's not just about incompleteness that you have data, but maybe not some part, but just generally you have this problem and because of some parameters and constraint of the problem, you just
Yeah,
have 20 data.
yeah,
No, I think like there are some work, in Texas A&M and I think in Ohio State, and they're looking at, this domain transfer, right? And
yeah,
I think like some of those works is really trying to touch on how can we build these models that can be to some to some extent
okay,
generalizable when you have very limited data.
yeah,
I think it's an exciting research domain. If you look at that domain transfer, basically the idea is that, well, is my problem similar to a different problem that we have more data and I can get some of those models and bring them. And this is was, some of the earlier computer vision things were,
yeah,
I think you know better than me, right? But like they were trying to do this kind of domain transfer, right?
yeah,
The whole COCO movement and those things. And I think it was very successful for them. So I'm pretty excited to see if in the engineering community we
yeah,
can do some good domain transfer and bring those models from the
yeah.
problems that we have more data to the problems that we have very, very limited data.
Yeah, thank you so much. I agree on that because whenever I come to these topics, most people ask what is next. I think this can be something next that people can
Oh yeah.
think about it. So any other questions? If yes, raise your hand, open your mic. I will wait for instance 30 seconds for that. Hmm. Okay, I think we are done with the question. I want to thank you so much for this fantastic presentation, and I'm sure that all the people who has attended enjoyed a lot. I want to have your permission. If anyone has a question, they can reach out to you by your email if it is fine. So I think Robin has also put your email there. Thank you so much for that, Robin. By this, I think we can move to the next step. Thank you, Dr. Salamati.
All right, thank you so much. And I just, as a last comment, please, not only you have my permission, I encourage you, please reach out if there's any question, if it can be helpful to your research or hear about your things, I will be happy to help. But besides that, thank you so much, Paisa. Robin, everybody, GSC, thank you for being here, and I appreciate
Yeah.
the time and opportunity. Thank you.
Thank you
Bye.
so much.